for inviting me here. And this is my first time in Korea, and it has been really nice to be here. Okay, so because I guess most of you are not birational geometers, I try to be not very technical. So I talk about this Iitaka conjecture. In dimension 6. So the fact that I talk about dimension 6 is not really very important. So I just want to show that there is a method which works in this case and possibly in many other cases where other methods don't seem to work. So that's the important message. Okay, so in general, it's suppose that first let me say that everything is over the complex number. Suppose that x and z are smooth projective variety. So most of the time I just talk about smooth, but actually we also are interested in singular cases. So suppose that we have these two smooth projective varieties, and suppose that they are somehow related. Then it's very important to find a relation between the canonical divisors of x and z. So this is a vague statement. So, in birational geometry at least, this canonical divisor played a very central role. So, a lot of things are discussed in terms of this canonical divisor or canonical bundle, if you like. So, it's important to somehow to be able to relate these two divisors. So, of course, a very basic example is when when dimension of z is just dimension of x minus 1. So in other words, this is a smooth divisor inside x. So in this case, there is a very simple formula. So kx plus z restricted to z is kz. But in most cases, I mean, this is something very simple. In most other situations, we don't have something simple like this. So it's more complicated to relate these two things. So the Iitaka conjecture is about, again, in somehow trying to relate these canonical divisors where the situation is different. So now, suppose that we have f from x and z, so x is smooth projective variety. Suppose this f is, this is just a projective morphism and with connected fibers. Okay, so let me also put surjective. Well, if the fibers are not connected, of course, you can take the Sten factorization and then up to birational, I mean, you have to blow out something. Then you get to a situation where the fibers are connected. Then this thing is called, an algebraic fiber space. And then the Iitaka conjecture tries to relate the canonical divisor of z and x in this situation when you have algebraic fiber space. So Iitaka conjecture that if we have a algebraic fiber space, then we have something like this. So I will need to define this invariant. So say that the Kodaira dimension of x is more than or equal to the Kodaira dimension of f plus Kodaira dimension of Z, where F is a general fiber, or just you can take a generic fiber. Okay, so I will define in a minute what is Kodaira dimension. But so the Kodaira dimension is defined in terms of this canonical divisor. So this is, it somehow tries again to relate the properties of the canonical divisor of X, the fiber, and the base, which is Z. So this conjecture was still is quite important, and it's motivated a lot of developments in birational geometry. Okay, so let me define. In general, suppose that D is a Caucher divisor with a normal projective variety. Then we define the Kodaira dimension of D like this. Okay, first, for any multiple of this divisor, you have a linear system. And if this linear system is not empty, you can define a rational map using this linear system. So, then if M times D, or you can write like this, if this has sections, then we get a rational map like this. So it defines from T to the projective space of the section. So it gives you a rational map from your variety into some projective space. Okay. And then the Kodaira dimension will be the maximum of the dimension of the image under all these maps. So if we have sections for some n, then we put the Kodaira dimension of D to be the maximum of the image under all these rational maps. Oh, sorry.
In the Iitaka's conjecture, is there some example having the equality phase?
Well, equality phase, yeah, of course, in some cases, it's just this doesn't mean anything. For example, if this is a rational, just P1, for example, and the fibers are could be of general type, but X itself, it doesn't have to be something rational, or it could have a non-negative Kodaira dimension. So yeah, of course, there are a lot of cases where this is not equality. Okay, so now for some divisors, of course, it may happen that you don't have sections, even if you multiply by anything. So the m's are always positive. In that case, we put the Kodaira dimension just to be minus infinity. Put so you see this from the definition that the Kodaira dimension is minus infinity, 0, 1, up to the dimension of the variety. So you don't have so many choices. And in a sense, this plays the role of, well, not entirely, but it's something similar to genus in the case of curves. It's not really true.
The notation is a bit strange, I would say. Chi of D means something different than chi of X, although D may also be a variety or something.
Yeah, okay.
Because
so
chi of
it's
X
a bit,
all the canonical divisor.
That's right.
Yeah.
So I mean, the correct thing, would be to put also the t here.
Yeah,
So
but
it
I mean,
depends.
chi of x is something different.
Yeah, it's something different. So yeah. So maybe if you liked, you can show. Yeah, of course this is a better notation. So it's different. When we talk about the canonical divisor, the Kodaira dimension of x, we don't mean it's a divisor on some variety.
So then you mean d is equal to canonical.
Yeah, exactly. So then we also define Kodaira dimension of your variety to be Kodaira dimension of the canonical device. So of course there are certain technicalities here. This needs to be Carty or at least Q Carty. And so I assume that D is Carty, but actually it's, you can also define it when it's a Q divisor or a Q Carty. You can take some multiple, make it into something integral, and then talk about this thing. So it also makes sense in those cases. Okay, so the Kodaira dimension of the variety is just the Kodaira dimension of the canonical device. Yeah, okay, maybe I put also his question just as an example. So, for example, if just take P2 and take a pencil, like a left-shot pencil, for example. Of curves of high genus. And then put x to P1 to be the left-shot vibration given by this thing. Then, of course, what we have here is that the Kodaira dimension of x is just minus infinity. Kodaira dimension of the fiber is equal to 1. Kodaira dimension of the base P1 is also equal to minus infinity. So, I don't know if you like to call that equality, that minus infinity equal to 1 plus minus infinity. So in general, when the varieties are rational, or when the canonical, when the Kodaira dimension is minus infinity, this is not interesting. Okay, so maybe I mentioned just some known results. So one of the most important results is by Kawamata, which says that if F, the general fiber, has a good minimal model, so I hope to talk about this thing in a bit. If this F has a good minimal model, then the Iitaka conjecture holds for this case. And again, Kawamata has proved the case when dimension of z is equal to 1. So the base is just a curve. And Vivek proved the case when z is our general type. So to be of general type simply means that the Kodaira dimension of z is equal to its dimension. And then finally, Kola also proved that if the fiber is of general type, the generic fiber, then again the Iitaka conjecture holds. But Kola's result actually follows from this one, because now we know that if F is of general type, then we always have a good minimum model. So then this Kola result immediately follows from Kawamata's result. So all these known results are essentially based on analyzing certain sheaves. So to be more precise, these are based on semi-positivity properties of looking at sheaves like this. So you take the direct image of Ox m times k of x minus the pullback of the canonical divisor of z. Yeah, well, if you like, you can also write it in this form. So the idea is to look at these sheaves. These will be torsion-free sheaves on the base, and then try to prove that this is semi-positive, or at least in a generic sense, it is semi-positive. And then, so the idea is to construct a lot of sections for this. And if you have a lot of sections for this, then you just tensor with omega z to the m, and then you should also have a lot of sections for omega x to the n. But in the situation that I will talk about, this simply does not work. I mean, this semi-positivity, I mean, it doesn't work. But of course, the idea is again to look at this kind of sheet. Okay, so the main result here is that so this Iitaka conjecture holds if the dimension of x is at most 6. Okay, so I have to talk about a few other technicalities before I can go into the proof. First, let me talk about the Neff divisors. Okay, suppose that we have a Q-Cartier divisor. So Q-Cartier means that some multiple is Cartier. Then we say that this divisor is Neff. So of course, again, you are on a normal projective variety. So this is called Neff, or semi-positive, if the following thing holds: if intersection with any curve is non-negative. So by curve I mean just irreducible reduced subvariety of dimension 1. Okay, so now suppose that we have this divisor Neff on T, then there is a certain reduction map for Neff divisors. So from now on, assume that D is Neff. Then, so many people, so if I write the name of all of them, it will probably fill in the board, so I just say many people. So many people proved that if you have a Neff divisor on a normal projective variety, then you have a rational map with some very nice property. Then there is rational, okay, so actually almost regular rational map So the idea is like this: you have a Neff divisor, intersection with any curve is non-negative. Now, in general, it's quite hard to see where exactly this divisor intersection is 0. So we are interested in on those curves where intersection is 0. But this result says that you can define almost regular map. So almost means that this will be, so it's a rational map, but it's not defined only on some small subset, such that if you have any curve which does not intersect this bad subvariety, then the intersection of D with that curve will be 0, and you can contract those curves. So it's contracted by this rational map. So you have a rational map, let's say pi, from T to S, such that so almost irregular means that at least some fiber is projected. That means that the place where this rational map is not defined will not intersect some of the fibers. Well, you can also talk about it in like take a birational map, make this into a regular map, and then some of the fiber will not intersect the exceptional divisors in that way. Okay, so you have an almost regular rational map such that if F is a projective fiber, so projective fiber means one of those good fibers which does not intersect the place where this is not defined, then the restriction of the divisor to this F is simply 0, at least in a numerical sense. And if you have any curve, so if you take any point very general, then and see a curve passing through this point, such that pi of C is not a point, then the intersection of D with this curve must be positive. So in a sense it says that you are almost contracting all those curves where D is 0. If there is a curve, of course in a very generic sense, such that this curve is not contracted, then the intersection number must be positive. So anyway, this map is called the reduction map of this Neff divisor. Because one of the big difficulties in minimal model programs, especially this conjecture called abundance, is that when D is the canonical divisor, conjecturally if the divisor is not big, then you must have a reduction map, non-trivial like this. But the problem is, even if you assume that the intersection with any curve is positive, we still cannot prove that. So essentially that should imply that the divisor is ample. But we cannot prove that. Okay, so anyway, using this reduction map, we can define the Neff dimension of this divisor. So this is defined as the dimension of S. So of course this is dominant. So in particular, if S is a point, this will imply that this divisor is completely numerically trivial. Okay, I will.
Excuse me, I can't read. The Neff dimension of L is alignment or?
Oh, sorry, this is D.
D,
I will check.
Yeah, then it's better.
Yeah.
Okay.
Yeah, thank you.
It's the dimension of...
Next dimension of D.
No, on the right-hand side, dimension of rho.
No, this is S.
The fiber.
Not the fiber, it's the image, it's the variety you obtain.
Of S, I see. Okay, thank you.
Yeah. So
Yeah.
so for example, if you don't have many curves with zero intersection, then the nth dimension is just equal to the dimension of the variety. Okay, so I will need to talk about also a conjecture of Campana-Peterson, which is related to this whole story.
So this nth divide, dimension of a nth divide is the same as the Kodaira dimension?
No, it's not. Of course, that's abundance, but in general, not. So in general, the Kodaira dimension of D is not equal to the nth dimension of D. But if D is the canonical divisor, then of course that's abundant. So that's expected only in the case of canonical divisor. There are easy examples in dimension 2 where the divisor has nth dimension 2, but the Kodaira dimension is even minus infinity. So you don't have, the Kodaira dimension will be 0. So it's quite easy to construct. For example, you can take some elliptic curve and then take a certain locally free sheaf which is indecomposable, and then take the projective space of this guy and take a section. In some situation you can take the section such that the section will be taken as D. In that case, intersection number of D with itself is 0, but with any other curve is positive. But Kodaira dimension of this thing is equal to 0. Yeah, anyways. Okay, so there is a conjecture by Campana and Peterson which says that suppose that T is well, in my case I need only smooth. Anyway, suppose that this is a smooth projective variety such that the canonical divisor can be, in a numerical sense, can be written as A plus M, such that this is effective and this is pseudo-effective. So pseudo-effective means this means limit of effective divisor. Where this A and M are only Q divisors. So suppose that in a numerical sense you can decompose K into something effective and something only pseudo-effective. For example, NEF is always pseudo-effective, so that's one candidate. Then they conjecture that the Kodaira dimension of this divisor must be at least as much as the Kodaira dimension of A. Or, yeah, this is by definition the same as Kodaira dimension of T. This must be more than or equal to the Kodaira dimension of A. Well, of course, this is a very difficult problem because it contains abundance as a very special case. So that means that this is not easy to prove. But at least they proved it in one special case. And this special case is when M is just numerically trivial. So it's not trivial, but just in a numerical sense it's trivial. Yeah, so they use some result of Carlos Simpson on abelian varieties to prove this thing. Okay, so how much time I have? Half an hour?
Yeah, no.
Okay, so I also very briefly mention about this minimum model stuff. Okay, suppose that we have a smooth projective variety. Of course, the minimal model program is discussed in much more generality, but anyway, I guess this is the most understandable. The minimal model conjecture says that we have the following thing. So it says that there is another projective variety which is birational to T and with some very extreme properties. T prime birational to T such that so either the canonical divisor of this is NAP, so in a numerical sense it's semi-positive, or this T prime has a Fano fiber structure. So this last part means that you have a map to another variety, let's say prime Zegon, such that the dimension of this is strictly bigger than the dimension of T Zegon, and the general fibers are fun. Well, here you can think about T prime to be smooth, but of course in almost all cases this is not smooth. But it has singularities, but the singularities are sort of understood. So you have these two extreme cases. Either you get something like positive or something. Now, so we call this, so if we have the case when this is NF, this thing is called a minimal model. And we say that it's a good minimal model if this divisor is semi-ample. Semi-ample here simply means that some multiple of this is generated by a global section. So this part is called the minimal model conjecture, but this part, existence of a good minimal model, is called the abundance. So if you like just. So anyway, these are the most fundamental problems in rational geometry. Okay, so if you remember, I mentioned the result of Kawamata. We say that if in the Iitaka conjecture, if the generic fiber has a good minimal model, then the Iitaka conjecture holds. But unfortunately, these two conjectures are known only in very special cases. So for the moment, we cannot use it in all cases. Anyway, so let me go to the proof of the main theorem. Okay. So actually, most of the cases follow from Kawamata's result, but there is one case which no other method seems to work. And so this is the main case is this. Suppose that the Kodaira dimension of f is 0 and dimension of z is 2. So of course dimension of x should be 6. So dimension of f is then 4. So this is the case where no other methods work. So I explain this thing first. If there was any time left, I will talk about the other cases. So we have a 6-fold which is fibered by, in a generic sense, by 4-fold, such that the Kodaira dimension of the generic fiber is equal to 0. And then, so the Iitaka conjecture says that the Kodaira dimension of x must be more than or equal to this thing, which is just 0 plus Kodaira dimension of z. So we should prove then that the Kodaira dimension of x is more than or equal to this thing. So as I said, this is just 0 plus Kodaira dimension of z. So now I use the result by Fogino and Mori, which is a general version of Kodaira's canonical bundle formula. So this canonical bundle formula says that we have the following set. So we have a commutative diagram like this. So we have x to z, this is the original thing. This says that up to birational changing, so it means that up to some birational mass like this, there are certain very good things happen. This is G, this is sigma, and tau. So we have a commutative diagram like this, such that sigma and tau are birational. G is again another algebraic fiber space, but they are closely related in the following sense. But we have many also other good properties. So after this birational changing of the situation, then they say that moreover there are Q divisors B and L on the prime and R on X prime, such that, okay, I'd like to decompose this. So I write this R as its positive part minus its negative part. just decompose it. You have a Q divided. It has one positive part, one negative part, and just write it like that, such that we have these properties. First of all, this B is effective, and second, L is a net divide. Then the shifts are also, well, the divisors are related like this. Okay, well, let me come here first and also introduce this notation. Suppose that P is the smallest number such that the direct image of this sheaf is non-trivial. So because the Kodaira dimension of the fiber is equal to 0, then of course you always have some number like this. So there is some number such that the direct image of this thing is not trivial. Okay, so what happens in this case? P times k of x prime is equal to P times the pullback of k of z prime plus b plus l, and then finally you need to add this correction term r. So in the classical Kodaira's canonical bundle formula, you don't have this thing. You have just an elliptic fibration, and you don't need to have this thing, because you have a numerically trivial situation. But in this case, we only know that the fibers have Kodaira dimension 0, so we don't have necessarily numerical trivial situation. So you need to put a correction term here. But these are also satisfy some, again, nice property. So what happens is that for I divisible, so that means that if you take some large number with a lot of divisibility properties, then the push down of this sheaf is just equal to 0. So this is trivial, not 0, just trivial. And also we have some properties for the negative part. The negative part is in a sense very exceptional. So that means that this is exceptional over x. So that means that it's a divisor which is contracted by this birational map. But also in this direction it still is very exceptional in the sense that its image is not a divisor. So that means that the codimension of the image of the support of this R minus is more than or equal to 2. Yeah, so it's contracted in this way, but you have a fibration here, but even in that sense, again, it's some sort of exceptionality here. Okay, well, now if you look at this formula, then what we are interested in is to construct sections for this. If this Kodaira dimension is not negative. So, of course, in that case, everything is just a trivial statement. So you can assume that because if this is minus infinity, then there is nothing to prove. So you need to construct sections for this. But if you want to have sections for that, you need to construct sections on this side. So I'm going to use all these properties to construct actually sections here, and then say that it also gives you sections for this on the left side. Okay. Well, anyway, so especially from these three properties here, so we deduce that So they show that actually the space of sections for p times kx is equal to, well, probably better if I write something like this. So we have plus r minus here, and here we have just r plus. Okay, so because this guy is exceptional, so the sections for this will be the same as if you go down on x. But if you go down on x, the push down of this is just p times kx. So this is the same as p times kx prime plus r minus. Well, I better also put some multiple here. Okay, then I can also now look at this side. But if you use the projection formula, you can actually just ignore this part because of this property. So the direct image of this part will be just trivial, so you can forget about it. So the important thing is this part here. So this is equal to the space of sections of I times p times, yeah, so I can just consider this divisor. So I want to get sections here, then I should try to prove that I have sections downstairs with Z prime. Okay, so here we have a couple of different situations. So if the Kodaira dimension of Z prime is equal to 2, or if the Neff dimension of L is equal to 2, so if the Kodaira dimension of Z prime is equal to 2, that means that this divisor is a big divisor. It's when you multiply by large numbers, you will have a lot of sections. So the main problem here is that you have a divisor which is Neff, but Neff does not mean that you can have sections even if you multiply with very large numbers. So the idea is that to pair it, this L with K, and then to construct sections. Well, if the Kodaira dimension is 2, this is a big divisor, then you can extract some ample part and give it to L. And when you do that, you can also construct a lot of sections. So this is not difficult to see that this will have a lot of sections. And also, if the Neff dimension is equal to 2, then Ambro also analyzed this situation and see that this has a lot of sections. So you essentially just use the Riemann formula. Anyway, this is not difficult to see that in both cases, then this divisor will be big. So big simply means that its Kodaira dimension is 2. Well, this also implies that the Kodaira dimension of x is equal to 2, and therefore we are done in this case. So the Iitaka conjecture in this case says that the Kodaira dimension of x is more than or equal to the Kodaira dimension of z prime, or which is equal to the Kodaira dimension of z. But this Kodaira dimension is, the maximum is 2, so you cannot just have more than that. Okay, so that we can forget about these cases. Now, the problem is if the Neff dimension is not equal to 2. But in that case, we also have some nice things happening. So if the Neff dimension of L is equal to 0, then that means that L is numerically trivial. So at least in a numerical sense, it's just an effective divisor. But if the Neff dimension is equal to 1, then the results of those people who proved the reduction map shows that then the reduction map will be actually just a regular map, not only almost regular, but it will be regular. So the reduction map for this L, which is a map from the prime to some S, is regular, and moreover we have the following thing. So there is some divisor on this. So in this case this is a surface, then S will be a curve. Then we have a divisor on this curve which pulls back to L in a numerical sense. So there is a divisor, let's say the prime on S with positive degree such that, well, I could just say effective divisor. It's not really a divisor, but Q divisor. So we have an effective Q divisor on S such that in a numerical sense L is just the pullback of this device. So in any case, in both cases when the Neff dimension is 0 or 1, up to numerical equivalence you just have an effective divisor. But as I said, this does not immediately give you sections. I need to use the result of Campana and Peterman to construct sections.
So where do you need it? Dimension X is 6?
Dimension of
X is 6? What do you use?
so the thing is that if it is not 6, then you can use other arguments. The conjecture follows from minimal model product. But when dimension of X is 6, so your fiber is here of dimension 4, and the Kodaira dimension is 0. In this case, we know that this fiber has a minimal model, but we don't know if it has a good minimal model or not. So we cannot use the, yeah. But anyway, what I have written here actually doesn't use the fact that the dimension of X is 6. What you need is only that the fiber has Kodaira dimension 0 and the base is a surface. So actually work in any dimension. Okay. So by the properties of this whole situation, then we have something like this. We have the space of sections of I times P times K, Kx plus M. So let me define what is M. So I put M to be the push down of the pullback of this divisor L minus this. To be consistent with my notation, let's put D minus. Okay, so suppose that we have this M. Now this M is actually, in a numerical sense, is trivial, but as a divisor we don't know if it is trivial or not. Then what we know is that the space of the sections for this is equal to the space of sections of, so I just replace L and replace L by D. Then I have IP times K Z prime plus I have then G star of D minus L, so this is X prime. This is IP times K of X prime plus the fullback of D minus L then I also need to put I times R minus 1. But anyway, this is equal also to the space of sections of IP times KZ prime plus B plus D. So what I have done is just I try to replace L by this D. So L I know is a numerical, is a Neff divisor, but at least I know that D is an effective divisor, not only Neff. So because this is effective, then I can construct sections here easily. And therefore by Campana-Pitano, so I have my divisor plus something which is numerically trivial. So Campana-Pitano then say that the Kodaira dimension of K is actually more than or equal to the Kodaira dimension of this thing. So Kodaira dimension of X is more than or equal to the Kodaira dimension of Kx plus M. But this thing is, because we have the same type of sections, so they also have the same Kodaira dimension. So this is just the Kodaira dimension of Kz prime plus D plus D. But this B and D are both effective divisors. So if you add some effective divisor to any other divisor, the Kodaira dimension must not decrease. At least it should. It may be the same, but it will not decrease. So this is more than or equal to the Kodaira dimension of Z prime, but this is the same as the Kodaira dimension of Z. So anyway, the whole thing says that the Kodaira dimension of X must be at least as big as of the Kodaira dimension of Z. So this will then imply this case. So how many? Finish?
Maybe 2 minutes. Maybe you can finish or just.
Yeah. So actually, this main part is already
maybe
finished.
there is some application.
Yeah. Okay. So this will settle the case when we have the situation that I mentioned at the beginning. But there are other cases still left. Well, if the dimension of Z is equal to 1, so we have curve, then we can use a result of Kawamata. Okay, so that we don't have to worry about that. Actually, it works in every dimension, so especially in this case. But if the dimension of the fiber is less than or equal to 3, we can use the minimal model program. So it left to deal with the case when the dimension of the fiber is 4. But in this case also we have several cases. If dimension is 4 and if Kodaira dimension of the fiber is positive, then we can actually again use this minimal model program. So the only case left is dimension of F is 4 and Kodaira dimension is 0. But that's what I just discussed before. Yeah, anyway, so the important thing is that I think this method works if the base is an abelian variety. So at least with Campana we analyzed several cases and it seems to work. I think some maybe hard work we should settle this conjecture when the base is abelian variety. Okay, I will stop.